Hello, this is the second video in the second vector series for OCR AS Core Pure Further Mathematics, and it covers the vector equation of a line in 3 dimensions. The vector equation in 3 dimensions has the same form as in 2 dimensions, r equals a plus lambda d, where a is the position on the line that we are jumping to from the origin, lambda is the variable parameter, and d is the direction of the line. For example, r equals 2i plus 4j plus 3k plus lambda I minus 4k can also be written as 243, or a, plus lambda 1, 0, minus 4, or d. This can be amalgamated to give r equals 2 plus lambda, 4, 3 minus 4 lambda. A simple sketch is a good idea and may help you to remember what this is all about. Just try and imagine this in 3D rather than in 2D. R is not mysterious, it's just finding the coordinates x, y, z of any point in the line. Here the 2 plus lambda, depending on the value of that parameter lambda, would give you the value of the x-coordinate. The y-coordinate would be 4 and the z-coordinate would be 3 minus 4 lambda. You may wish to use a dynamic program such as GeoGebra to visualize these lines in 3 dimensions. In this example here, we need to show that the point 5, 4, minus 9 lies on the line r equals 2i plus 4j plus 3k plus lambda I minus 4k. Let's write r in the form we used previously, or 2 plus lambda, 4, and 3 minus 4 lambda. If we can show that for some value of lambda this equals 5, 4 minus 9, then we will have shown that that point lies on the line. So 2 plus lambda equal to 5 would imply that lambda equals 3. Let's check the z component. 3 minus 4 times 3 would indeed give minus 9. Therefore, we have shown or verified that the point 5, 4 minus 9 lies on that line when lambda equals 3. In this example, we're asked to find a vector equation of a line through A and B. First of all, let's work out the vector AB. This would be B minus A, or minus 4, 2, 1, minus 2, 4, 3. Which would equal to minus 6, minus 2, minus 2. If we wanted to, we could take a multiple of this line, and 3, 1, 1 would be a nice tidy multiple to use. We then need to pick a point on the line and write the equation. You'll notice it's an equation, as this will not be unique. So I'm going to choose A as my stepping on to the line point, and then I'm going to have the parameter times the direction vector, which I'm choosing as 3, 1, 1. This is therefore an equation of a line through A and B. It is not unique. I could have chosen to jump onto the line at B and then used a different parameter, call it a different letter, and a different multiple of 3, 1, 1. Whether we are in 2D or 3D, the angle between two lines is the same as the angle between the two direction vectors of the lines. You may remember that in previous series we have looked at finding the angle between two vectors using the scalar product. Here we're asked to find the acute angle between the lines L1 and L2. For L1, r equals 2i plus 4j plus 3k plus lambda I plus 4k, and for line 2, r equals minus I plus 2j plus k plus mu of I plus 2j minus k. You will note that different letters are used for the parameters to avoid confusion. The two direction vectors are therefore 1, 0 and 4, and 1, 2 and minus 1. Taking the scalar product, that gives us 1 plus 2 times 0 is 0 plus 4 times minus 1, which is minus 4, or minus 3. You will remember that cos theta equals the scalar product A dot B over the magnitude of a vector A times the magnitude of a vector B. So in this case, it is minus 3 over the square root of 1 squared plus 4 squared times the square root of 1 squared plus 2 squared plus 1 squared. We find then, if you use your calculator using the cos to minus 1, if your calculator is in degree mode, you will find that theta is approximately 107 degrees. If we look at this in a little diagram, and we have L1 and L2, then you'll note that the acute angle must therefore be 73 degrees. So the acute angle will be 73 degrees. In the next session, we will work out how to write the equation of a line in 3 dimensions in Cartesian form.